Okay, so this is the last presentation in this session. So this presentation will be given by Abel Souza. So Abel Souza is a postdoc at the University of Massachusetts in Amherst, and he will be looking for academic positions this coming fall. So Abel, it's all yours.
Hi, everyone. Today I'm presenting the Ecovisor, a virtual energy system for enabling carbon efficient applications. So we all know we have a sustainability problem, right? Like hyperscale data centers have been doubling in capacity of roughly like at every 4 years for the last decade. And this is primarily due to artificial intelligence and machine learning workloads. The energy use of these data centers, depending on the report that you look at, it's around 2 to 5% of the world's consumption. I'm not sure what. Oh, okay. Yeah, as I was saying, the energy usage of data centers depend on the report you look at. It's between 2 to 5% of the world's consumption. And because this is an exponential growth, people are actually worried about the environmental impacts that this is causing. But as counterintuitive as it sounds, the rise in cloud energy use is not really the issue. The issue, and in fact, is that the carbon emissions from these energy use is the problem, and the negative impacts of this is that it is causing, it's the main problem in the environment. So, as it was pointed out in the previous presentation, like a distinguished characteristic of renewable is that it's very, it's unreliability, it's intermittent, and not available in the unlimited quantities at any point in time or in any location. So, and it also varies based on what is happening to the grid system. So, like in the former case, like the power generated by zero carbon renewable energy sources, like mostly from solar and wind, it's very unreliable because it depends on weather conditions and environment conditions. And in the later case, the problem is how with the grid is volatile because it varies based on the carbon emissions of the different sources that are supplying energy to the system, and also on the demand that is happening in the system. So the takeaway here is that clean energy is unreliable and varies both temporarily and spatially. But despite this unreliability, like compute is well positioned compared to other industries to tackle this problem and reduce their emissions by transition to clean source. For instance, computing has many like spatial, temporal, and performance flexibility. These features would enable applications to shift location, time, intensity to actually better align its execution with the availability of low carbon or zero carbon renewable power. Moreover, like computation can also like leverage numerous software based fault tolerance techniques, include checkpoint and restart, replication, recomputation, to continue like its execution despite unexpected variation in availability of low carbon energy. But the thing is that to effectively make use of all these features, application actually need visibility of into the grid system. But energy operators have traditionally and implicit exposed just a very simple reliability abstraction. The abstraction of a reliable supply of power that varies depending on the demand And it's represented by this power socket that is very simple interface. But besides, in many cases, like today, the grid system includes connection not only to the grid, but to various sources of energy, like that usually include energy storage, like batteries, solar, wind. So the takeaway is that without the visibility into the grid's reality, application cannot really influence their own energy and compute demand. So our solution to this lack of grid information, it's pretty simple. Like we propose a system capable to monitor and grant visibility through software-defined controllers to applications. And this through a very simple API that we are calling here Ecovisor. The Ecovisor is akin to a hypervisor, but it also virtualizes the energy system and exposes this to application. In this way, we enable applications to monitor the energy and carbon, besides controlling where the energy they are using will coming from. For example, such as the grid or a battery or a nearby solar array. This concept is similar to how applications are currently allocated virtual resources in the cloud, but the Ecovisor also exposes energy allocation controllers to applications. The takeaway, again, is very simple. The visibility and control of the energy system will allow applications to monitor energy use, track emissions, and select renewable source as they see fit. So the figure here is showing the Ecovisor architecture. It bridges and exposes real-time energy information by interacting with a container orchestration platform like LXD or Kubernetes. In our current implementation, we basically use LXD because it has some horizontal and vertical features that are very important to control energy use in real time. And applications will write their own policies, and these policies are enforced through C group controllers that LXD has. And it can work like locally, or if you have a larger cluster, it also supports this option out of the box. The control and monitoring functions are exposed through a REST API and wrapped around like CO2 signal. It's a third-party service from Electricity Map that expose carbon intensity information from various locations around the world. And together with the LXD API and software-defined power meters, so we know how much power applications are using. So the API is very simple and narrow by design, and it represents the minimal set of functions needed to control power supply and demand. I don't know what happened again. Oh, okay. So the control, get, and asynchronous notifications are like it's the foundation. So higher level libraries can use the Ecovisor to expose these functions to applications. So we chose also like container level APIs because with that we would enable the widest range of policies to be written. And importantly, like developers can use these functions to implement other higher level libraries that further simplify the interactions with the energy system, and it can also make it entirely transparent to developers so they don't actually need to do anything. So To demonstrate the benefits of this visibility exposition, like we deployed a real prototype that emulates a low-scale data center using various Raspberry Pis, all powered from various sources such as grid and solar, and all accessible through the network. We run several applications with 2 different policies, or with various types of policies. Like we have system level policies because these policies are basic application agnostic and do not use any information from about the application. No, it doesn't use any characteristics from the application to take decisions. And we compare this against using application characteristics, and we are going to show what happens to runtime and carbon emission results. So here we have, we compare 2 batch applications, a PyTorch ML training and an HPC application called BLAST. It's a bioinformatics application. Additionally, here we also compare the system application tailor policies against an agnostic policy that basically executes a job as soon as it's submitted. And you can see that like the system level policy is based on wait a while. It's a technique that basically waits like for the best period in a carbon intensity time series to submit a job. And the application level policy in this case here also uses these techniques, but because it has knowledge about scaling characteristics for the application, it scales when it submits the application for execution, it scales up by between 2 and 4 times the amount of resource that it originally had. And this is just to make the application runs faster so it can take advantage of low carbon periods better. So we evaluate the total runtime and carbon emissions for system for these 2. And we can see that the Ecovisor, like it allows applications to better optimize their carbon efficiency compared to a policy, a system level policy that doesn't use any information from applications. And it enabled them also to have a trade-off in runtime and carbon emission. And it can also find the best scaling factors when we are developing and creating your own policy. Next, we consider another policy for web applications. It's the system level policy. Again, it's agnostic to what the application does. And it basically enforces a carbon budget for the application by it tries to rate limiting the carbon emissions at all moments in time. So this technique is also known as carbon capping. So we compare this again against application-specific policy that uses a more flexible strategy, and it uses carbon budget, and it can compare to the system policy. It can also emit more carbon at some specific moments just to control its SLO. So the application, again, as a result, like compared to the system level policy, the application tailor policy would allocate the minimum amount of resource such that SLO can be satisfied. And yeah, we showed that this dynamic budgeting for policy provided better performance during periods with high intensity in carbon and also in the workload. And it also achieved 23% higher savings on top of the system level policy. So that's was a good result. So in conclusion, like the use of visibility and control enabled by the Ecovisor can provide significant benefits to applications in terms of efficiency, and also performance, and of course, carbon savings. So by leverage all these exposed functions, applications can make informed decisions about the energy use and reduce the footprint. Because we think they are better positioned to take their own decisions because they know exactly what is needed and when it's needed to adapt to change in system resource. So we see the Ecovisor as a foundation for even more carbon efficient applications in the future. Higher level libraries, of course, can offload energy decisions from the applications, and together with new abstractions, the development of carbon efficient applications can be simplified even further and be transparent to the users and developers. So our ongoing work is focused on exploiting temporal and spatial flexibility to further reduce carbon and develop new abstractions. So thank you.